Okay, so now that you have some time to think about this question, which one falls to the ground first? Let's address this. And this is one of the most important facts about the property of weight. Okay, no matter whether you're on Earth or on Mars or any other planet, right? The gravitational force, remember, weight is the gravitational force on an object due to the planet, right? It belongs to this fact. What did you guess? Now, intuitively, this is one of the most counterintuitive things in physics, but some of you might discover this even at a very early age already, and some of you, this might be one of the most important revelation of your life, that you realize that actually both objects fall to the ground at exactly the same time. And I'll repeat that. No matter how, I don't like to use the word heavy, but let me temporarily use it. No matter how heavy that is, and like if you hold it on your hand, one weighs so much more than the other, they will fall to the ground exactly at the same time if you release them at the same height. Okay. I'll see if at the end of this lecture, if I can do a quick demonstration over here. I'm limited by being locked in the pandemic, but I'll see what I can put within my office and see if I can demonstrate this, or also link you to other great videos around on the internet, or you can find some and share them on Piazza if you find them, if you find some interesting ones of these experiments exactly showing this. Okay. So let me reiterate this, right? So they arrive at the ground at the same time. And I'll write that down in a second. And in Piazza, I also prompt you to think about why that is the case, okay? And that is in some sense a trick question, because if you can come up with a reason why, you probably have solved one of the greatest mysteries in physics. In fact, I don't know if this is something even rarely talked about in textbooks, is no one actually knows why. This is one of the deepest questions of modern science, of why these things are the same. Now, we have a formula that I'll show you, and we can calculate things, but the question of why is very, very difficult to answer. And I'll address that in a more formal way in a second, okay? So, slightly trick question. I enjoy reading a lot of the potential guesses, very good line of thinking. This is actually, even till this day, you probably are not expecting this, even till this day, we don't know why all these objects fall the same way. And people have measured this to incredibly strong accuracy, great accuracy, and they still find no discrepancy. No matter how large the mass is and how tiny the other one is, they still would react exactly the same way under gravity. So this is truly one of the greatest mysteries. I'll clarify that in a second, but let me write this out. All objects, irrespective of mass, falls under the same acceleration. Due to gravity. Okay, so one of the most important facts in this course, and on Earth we have measured this. So this is a very special number, right? Because everything falls with the same acceleration, right? It means they start off from at rest, or start from a certain velocity, and they start to speed up, but they speed up with the same rate, okay? And that rate was measured for all different objects, and they come to the same number, obviously a very important number, and we give it a little g symbol, and that is, so that this, it is the number 9.81, okay? The unit is how much meters per second it changes per second. So of course we won't write it in this clumsy way. We'll write it as meter per second square like this, right? We'll talk more about this, but this is a very important number. Sometimes if we're lazy, we'll approximate it with like one significant figure and say it's roughly 10 meters per second squared. But if you want just one, most of the time, if you're a mathematician, you'll probably approximate it as 10 because you're not worried about the precision. But if you're doing physics, you want to be just a little bit more precise with that, because if you want to compare with experiments, you want to go a little bit more precise, and usually we do 9.8. So for all your homework problems or your exercises, tests, exams, and rest of physics, usually 9.8 is good. If you want to ensure a little bit more, 9.81, it goes on. It has very high degree of accuracy. You can look that up in the internet. All right. So there's a name for this constant, right? So it's a constant number. So this is called the acceleration due to gravity on Earth. Acceleration due to gravity on Earth. Okay, a very long name, but it is what it is. Sometimes just the gravitational constant, but that could be confusing, as we'll learn another thing later on. Okay, so sometimes just abbreviate that, called acceleration due to gravity. We understand it's on Earth. Okay, on Mars it's a different number. On the Moon, again, it's a different number. So things do accelerate slower on the Moon, for example, because we'll see why actually. But yeah, it's around 1/6 of this. So this is the number on Earth. Okay. So given this fact, all right, so like I said, we don't know why everything falls in the same way. We just know they do, okay? So given this fact, can we come up with a formula for weight, right? For the gravitational force, okay? So we can. Let's think about how we can do that, okay? So let's look at the formula for weight. Okay, so how would we do this? Well, guess what? This one, there will be a general theme coming up over and over again. We draw a free body diagram. Okay, so let's look at a falling object, right? So let's have an object. We have a ball that's just free falling, right? I toss it in the air and just let it go, right? So you've seen in some of your homework problems and etc. How to draw a free body diagram of that. So let's recap, right? All you have to ask is two questions: what's touching it and what's not touching it. All right, so let's say it's a relatively massive ball, and let's remove all the air, ignore air resistance. All right, so what's in contact with it? Exactly, nothing, right? Nothing is touching the ball. So is there any contact force? No, zilch, right? There's no contact force whatsoever. So the only force that I'm assuming it is, near the planet of Earth is the gravitational force pulling it downwards. Okay, so before I've used capital G, it's up to you. For now, since we've introduced the word, I'll use W for weight. So just as a notation wise, in the future, you're free to use G for gravitational force, W or F sub G. I think the textbook used that. There's good and bad for everything. The textbook used F subscript everything for force, so it reminds you everything is a force. To me, if you're drawing a free body diagram, everything is a force. So instead of the force of tension, force of gravity, everything is a subscript. And now if you resolve it into x and y components, you now have FGX, FGY, FTX, and it gets really convoluted for me, making things more fancy than they have to be. So to keep things simple, I just use, I think that's good enough. Right, W and G, I use them interchangeably depending on what I want to emphasize. All right, so I'm emphasizing it as the weight. All right, so that is the net force, right? So what do I learn from this? I learned that in this case, the net force on the object, on the ball, let's say, is W. All right. What else do we know? Well, Newton's second law tells us that from a lot of experiments, we know that the net force would create acceleration, right? Depending on the mass, okay? And in our situation, in this case, so in this case, our net force on the ball is W. So what can we do? We can say, well, let's apply some subscripts here just to make it clear. Is, right? So let's put mass of the ball, the acceleration of the ball, and the net force on the ball, right? So we take this generic Newton's law, right? So this is Newton's second law, which applies for all objects, right? And now we're applying it specifically to the ball, okay? And then let's find, what do we know? Well, we can measure the mass, etc. But in particular, we know that in this scenario, the net force on the ball is W, as I've drawn over here. So this is, I don't know what the mass of the ball is yet. I could measure it, but not just yet. And what is the acceleration, right? And I told you we've measured that is 9.81, right? So it's G, okay? All right, so just to emphasize the relationship here, right? So this is how we present physics steps, okay? So one thing that you want to learn in this course is how to write proper solutions. So like formal solutions in order to present this in a very logical way to others. And you see, the idea is always try to write vertically. Don't try to write horizontally, try to write vertically, because this is the way where people can, by people, I mean all your grader and your TAs can trace where every variable is, right? So net force in this case is W, very simple, right? You don't even need to add anything. The acceleration is G, and the mass of the ball is G, okay? All right, so let's also double check one thing, right? The direction of things. So because in principle, everything is a vector quantity. Sorry, these two are vector quantities over here. The mass is a scalar. So this has a direction. So this is pointing downwards, but that's okay because A is also pointing downwards. So this everything over here is pointing downwards. Okay, so both sides, the left-hand side is a quantity that's pointing downwards. This is pointing downwards. That's fine. So I'll just remind myself over there. Should you put a minus sign? Doesn't matter that much. So one way is you can say, let me define the positive as going up. In that case, your net force will not be W, because if you define that as up, then your net force would be minus W, right? Because or in full vector notation, if you want, right? Full vector notation, it would be like this, right? This is the number, and then so that's the magnitude, and then it's in the negative J direction, or in component form, right? So nothing in the X direction. On the Y direction, it's going down. So you can do this. I'll put that just as a side note. But let's just do it the more easier way is to split out the magnitude and direction, or in some sense implicitly think that way is positive. Okay, so I have that. So in fact, so this is the weight on the ball by the Earth, right? And this is just a constant. That is true for any object. So in fact, now you realize that this formula could be anything. I could have replaced ball with anything. So what I found is a general formula for weight. So the weight on anything by Earth is equals to the mass of that thing times G. And this is, right, so on a thing is the mass of that thing times G. So this is what you want to put it in a box and remember it. And of course, there's a lot of subscripts here. At some point, you'll just remember this. But here's a tip for you is a lot of times equations is one of the most confusing things in physics to a lot of people, right? And I'll tell you why it is confusing is because students would remember the equation without knowing what they mean. And they'll start plugging maybe this M into another M or this W into something other W. During the course, I'll point out these common mistakes. And where you'll be plugging in things when you're not supposed to. And that stems from you not remembering what it means, right? So this is fundamentally what it means. So just to make it less cartoonish, is the weight on any object is the mass of that object times G. Okay, so in your notes, you don't need to write this every time you solve a problem. And make sure I'm just not stepping on my mic. When you're solving a homework problem or exam problem, you don't need to write every subscript. But in your notes, at least have that one time, because you want to remember what each variable means in its full entirety, okay? So this is a force, so it's always on something, by something, and this is mass, which is just a property of that object, okay? Right, so that is the formula for weights. And in particular, just an extra comment to this is sometimes people justify that, sometimes people will explain to you that all things fall at the same acceleration on Earth because of the following justification. They'll tell you, all right, so the acceleration depends on the net force, right? But the net force, when something is in free fall, right? This is a particular situation. Let me write this down, called free fall. That means just freely falling without any other external influences. So the net force is W, and W has a formula, right? So it's mg, all right? So you have this, okay? And you look at this and go like, oh, well, I can cancel this. So the acceleration is g. Look, under free fall, so free fall in some sense is the definition is F net is equals to W only. Right? So whenever you have free fall, when the net force is W only, your acceleration is a constant, and it does not depend. It does not depend on the mass. The acceleration itself does not depend on the mass. Now, that could be an okay argument. In my opinion, it's very circular, because how do you get this formula in the first place? You're relying on the fact that you have observed this. This is an observational fact. Okay, so this is comment number one. And so it's a circular argument if you use this to justify why everything falls the ground.